Welcome! Today, we'll tackle an interesting problem, number 1171, remove zero-sum consecutive nodes from linked list. This problem is a great way to practice linked list manipulation and algorithm optimization. Let's dive in and explore the solution step by step. In this problem, we are working with a singly linked list where each node contains an integer value. Our goal is to identify and remove all consecutive sequences of nodes whose values sum to 0. After removing these zero-sum sequences, we return the modified linked list. If there are multiple such sequences in the list, we eliminate all of them. Importantly, if the entire list itself sums to 0, the result should be an empty list. This process helps simplify the linked list by removing any zero-sum subsequences while preserving the relative order of the remaining nodes. Let's look at the first example to understand this better. Here, the input linked list is 1, 2, minus 3, 3, 1. In this list, the sublist 1, 2, minus 3 adds up to 0. By removing this sequence, we are left with 3, 1. Notice that the relative order of the remaining nodes is preserved, and no zero-sum sequences are left in the resulting list. This demonstrates how we simplify the linked list by removing any consecutive nodes that sum to 0. Now consider another example where the input linked list is 1, 2, 3, minus 3, 4. In this case, the sequence 3 minus 3 adds up to 0 and is removed. After eliminating this zero-sum subsequence, the linked list becomes 1, 2, 4. Again, the process ensures that the relative order of the remaining nodes is maintained, and no zero-sum groups remain in the modified list. Finally, in the third example, the input linked list is 1, 2, 3, minus 3, minus 2. Here, the sequence 2, 3, minus 3, minus 2 sums to 0, so we remove it entirely. What remains is just the node 1. This example illustrates the importance of handling larger zero-sum subsequences that span multiple nodes. Additionally, the constraints specify that the list can have up to 10,000 nodes and that values range from minus 1,000 to 1,000. It's also crucial to account for edge cases, such as when the entire list sums to 0, or when there are overlapping zero-sum subsequences. These considerations guide us in building a robust solution that works for all possible scenarios. When considering how to approach this problem, we can start with a brute force method. The intuition here is straightforward. For every node in the linked list, we check all possible subarrays or sequences of consecutive nodes starting from that node. We calculate the sum for each subarray and, if the sum equals 0, we remove the corresponding nodes. While this method is simple and requires no extra data structures, its major drawback is inefficiency. Since we need nested iterations to calculate sums for all possible subarrays, the time complexity becomes n squared. Additionally, the repeated summation of overlapping subarrays leads to redundant calculations, which makes this approach impractical for larger linked lists. However, it does have the advantage of requiring constant space, as it doesn't depend on any auxiliary structures to store intermediate results. To improve efficiency, we can adopt an optimized approach using the concept of prefix sums combined with a hash map. The key insight here is that if the cumulative sum at two different nodes in the list is the same, then the nodes between these 2 points must sum to 0. This allows us to identify zero-sum sequences without the need for repeated summation. The steps for this approach are as follows. As we traverse the list, we calculate a running cumulative sum. We store the first occurrence of each cumulative sum in a hash map, with the sum as the key and the corresponding node as the value. If we encounter the same cumulative sum again, it means the nodes between those two occurrences form a zero-sum sequence. To remove these nodes, we simply adjust the pointers of the preceding node to skip over the zero-sum sequence. This process ensures that we only traverse the list once, resulting in a time complexity of n. However, the hash map requires additional space proportional to the number of unique prefix sums, leading to a space complexity of n. Despite this trade-off, the use of a hash map eliminates redundant calculations and makes the algorithm significantly more efficient than the brute force approach. Given these considerations, the optimized approach using prefix sums and a hash map stands out as the best strategy for solving this problem. Its efficiency and scalability make it ideal for handling large linked lists. Unlike the brute force method, which suffers from redundant calculations and quadratic time complexity, the prefix sum approach operates in linear time, (n), by directly identifying zero-sum sequences through prefix sum matching. This clever use of a hash map allows us to avoid repeated summations and ensures that the algorithm handles even large inputs efficiently. While the hash map does introduce additional space complexity, this is a reasonable trade-off for the significant improvement in runtime. Additionally, although this approach requires careful pointer manipulation and is slightly more complex to implement, its benefits far outweigh the costs. Ultimately, this method strikes a good balance between performance and simplicity, making it the most effective solution for removing zero-sum consecutive nodes from a linked list. This problem focuses on removing zero-sum subarrays from a linked list. A zero-sum subarray is a sequence of consecutive nodes where the sum of their values equals 0. Our goal is to create a modified linked list where no such subarrays exist. To accomplish this, we need to identify and remove these subarrays efficiently. For example, given a linked list, if there's a sequence of nodes that sums to 0, we would adjust the links to remove those nodes entirely. There are also edge cases to consider, such as when the linked list is empty, when the entire list sums to 0, or when there are overlapping zero-sum subarrays. These scenarios require careful handling to ensure the algorithm behaves correctly in all situations. To solve this problem efficiently, we use the prefix sum technique along with a hash map. The prefix sum represents the cumulative sum of node values from the start of the list to a given point. If the same prefix sum appears at two different indices, it means the values between those indices sum to 0, indicating a zero-sum subarray. To implement this, we start by initializing a dummy node that points to the head of the list. This simplifies handling edge cases, such as when the zero-sum subarray includes the head of the list. We also initialize a hash map, called prefix_map, to store the first occurrence of each prefix sum, and a variable prefix_sum set to 0. As we traverse the list, we update the prefix_sum with the current node's value. If this updated prefix_sum already exists in the hash map, it means we've found a zero-sum subarray. We remove the nodes in this subarray by adjusting pointers and also update the hash map to remove any intermediate prefix sums within the subarray. If the prefix sum does not exist in the hash map, we simply add the current node to the hash map with the prefix sum as the key. The traversal continues until we reach the end of the linked list. Once the traversal is complete, we return the modified list starting from the dummy node's next pointer. This approach relies on the key insight that repeated prefix sums indicate the presence of a zero-sum subarray. By leveraging a hash map, we can efficiently store and retrieve prefix sums in constant time, enabling us to detect and remove zero-sum subarrays without repeatedly scanning the list. Using a dummy node is another important aspect of this approach, as it simplifies edge case handling, such as when the head of the list is part of a zero-sum subarray. The hash map, in this context, is structured with prefix sums as keys and the corresponding nodes where those sums were first encountered as values. This allows us to efficiently adjust pointers and remove the zero-sum subarrays without additional traversal. Analyzing the complexity of this approach, the time complexity is O(n), where n is the number of nodes in the linked list. Each node is processed once during the traversal, and hash map operations for insertion and lookup are O(1). The space complexity is also O(n) in the worst case, as the hash map may need to store up to n unique prefix sums. Let's consider an example to understand how this works in practice. Suppose we have the linked list 3, 4, -7, 5, -6, 2. We start by adding a dummy node and initializing prefix_sum to 0 and prefix_map with an entry 0 dummy_node. This setup ensures we can handle any zero-sum subarray involving the head of the list. As we traverse the list, we update the prefix_sum and check for its presence in the hash map. If found, we remove the corresponding nodes, otherwise, we add the current node to the hash map. Continuing the example, as we traverse the linked list 3, 4, -7, 5, -6, 2, the prefix sum evolves as follows. At node 1 with value 3, the prefix_sum becomes 3, and we add this to prefix_map. At node 2 with value 4, the prefix_sum becomes 7, which is also added to the hash map. At node 3 with value -7, the prefix_sum returns to 0, which is already in the prefix_map. This indicates nodes 3, 4, -7 form a zero-sum subarray, so we remove these nodes by adjusting pointers. The traversal then continues. At node 4 with value 5, the prefix _sum becomes 5, and we add it to the hash map. At node 5 with value -6, the prefix _sum becomes -1, which is added as well. Finally, at node 6 with value 2, the prefix _sum becomes 1, and it is added to the hash map. After processing all nodes, the resulting linked list is 5, -6, 2, which is free of zero-sum subarrays. This demonstrates the effectiveness of the prefix sum technique combined with a hash map for efficiently solving the problem. To solve the problem of removing zero-sum consecutive nodes from a linked list, we start by defining the listNode class to represent each node in the list. It includes a value, val, and a reference to the next node, next. In the solution class, we define the method removeZeroSum sublists, which begins by creating a dummy node with a value of 0. This dummy node is linked to the head of the original list and helps handle edge cases, such as when the zero-sum sequence includes the head node itself. Next, we initialize two variables, prefix _sum to keep track of the running total of node values, and scene, a dictionary that maps each prefix sum to the last node where that sum was encountered. Then, we perform the first pass through the list. In this pass, we traverse each node, updating the prefix sum by adding the current node's value. At each step, we store the current prefix sum and its corresponding node in the scene dictionary. This ensures that we record the last occurrence of each prefix sum as we traverse the list, which will be important for identifying zero-sum sublists later. Now, we reset the prefix _sum variable to 0 and start the second traversal of the linked list using the dummy node. In this second pass, we again update the prefix sum by adding the value of the current node. For each prefix sum, if it has been seen before, we know that all the nodes between the current node and the last occurrence of this prefix sum must sum to 0. To remove these zero-sum nodes, we update the next pointer of the current node to skip over them, connecting directly to the node that follows the last occurrence of this prefix sum. This effectively removes the zero-sum sublist from the linked list. Finally, we proceed to the next node and repeat the process until the end of the list is reached. Once the traversal is complete, we return dummy.next, which points to the head of the modified linked list without any zero-sum sublists. Here, we start by defining a basic structure for our solution. First, we import the necessary classes and declare the listNode class to represent each node in the linked list. Each node contains an integer value and a reference to the next node. Then, within the solution class, we define the method removeZeroSum sublists that takes the head of the linked list as its input. To handle edge cases, such as when the entire list sums to 0, we create a dummy node with a value of 0 and link it to the head of the list. This ensures a consistent structure where even the head node can be safely removed if needed. Next, we initialize a hash map called scene to store prefix sums and their corresponding nodes. The prefix sum is a running sum of node values, which helps us detect zero-sum sublists. We also set prefix sum to 0 and start traversing the list from the dummy node using a pointer called current. During the first traversal, we calculate the prefix sum at each step and store the last occurrence of that sum in the map. This ensures that if the same prefix sum appears again later, we know it corresponds to a zero-sum sublist in between. The traversal continues until current reaches the end of the list. Now that we've completed the first pass, we reset the prefix sum to 0 and reinitialize the current pointer back to the dummy node for the second pass. In this pass, our goal is to actually remove the zero-sum sublists. As we iterate through the list again, we calculate the prefix sum at each step, just like before. However, this time, we use the scene map to jump directly to the node after the last occurrence of the current prefix sum. This effectively skips over any nodes that form a zero-sum sublist, as they are no longer part of the updated list structure. By updating the next pointer of the current node, we dynamically remove the unwanted nodes while maintaining the integrity of the linked list. Finally, once the traversal is complete, we return dummy.next, which points to the head of the modified list. This approach ensures that all zero-sum sublists are removed efficiently in 2 passes. In this problem, we are tasked with removing zero-sum consecutive nodes from a linked list. The goal is to identify and remove all subsequences of nodes whose values sum to 0. To achieve this efficiently, we use the concept of prefix sums. A prefix sum is the cumulative sum of node values as we traverse the list, and we use a map to keep track of where each prefix sum was last seen. Let's take the example input 1, 2, -3, 3, 1. Initially, the linked list looks like this 1-2--3-3-1. We start with a prefix sum of 0 and an empty map to store the prefix sums and their corresponding nodes. In the first pass, we traverse the list to build this map. Starting with a dummy node of value 0, we add its prefix sum to the map, so the prefix sum is 0 and the map contains 0, dummy. Moving to the first node with value 1, we add this to the prefix sum, making it 1, and update the map to 0, dummy, 1, node, 1. Then, at the next node with value 2, the prefix sum becomes 3, and the map is updated to include it 0, dummy, 1, node, 1, 3, node, 2. At the next node with value -3, adding -3 to the prefix sum brings it back to 0. Since 0 was previously seen at the dummy node, this indicates that the sequence of nodes from the dummy node to the current node sums to 0. We update the map to note that the last occurrence of 0 is now at node -3. Moving to the next node with value 3, the prefix sum becomes 3 again, and the map is updated to 0, node, -3, 1, node, 1, 3, node, 3. Finally, at the last node with value 1, the prefix sum becomes 4, and the map becomes 0, node, -3, 1, node, 1, 3, node, 3, 4, node, 1. This completes the first pass, where the map captures the last occurrence of each prefix sum. Now, in the second pass, we reset the prefix sum to 0 and traverse the list again. At each node, we use the map to skip over any zero-sum subsequences. For example, starting at the dummy node with prefix sum 0, we skip directly to the last occurrence of 0, which is at node 3. At node 3, the prefix sum is 3, so we move to the last occurrence of 3, which is node 1. At node 1, the prefix sum is 4, and since there are no further nodes, the traversal ends. The resulting list is 3-1. Now let's look at another example with the input 1, 2, 3, -3, -2. The initial state of the linked list is 1-2-3-3-2, with a prefix sum of 0 and an empty map for tracking prefix sums. In the first pass, we start with the dummy node, adding its prefix sum of 0 to the map 0, dummy. At the first node with value 1, the prefix sum becomes 1, and the map is updated to 0, dummy, 1, node, 1. Moving to the next node with value 2, the prefix sum becomes 3, and the map updates to 0, dummy, 1, node, 1, 3, node, 2. At the next node with value 3, the prefix sum becomes 6, and the map grows to 0, dummy, 1, node, 1, 3, node, 2, 6, node, 3. Then, at the node with value -3, the prefix sum reduces to 3, which was last seen at node 2. This indicates a zero-sum subsequence from node 2 to node -3. We update the map to reflect the last occurrence of 3 as node -3. Finally, at the last node with value -2, the prefix sum becomes 1, and the map updates to 0, dummy, 1, node, -2, 3, node, -3, 6, node, 3. In the second pass for this example, we again reset the prefix sum to 0 and traverse the list while skipping over zero-sum subsequences. Starting at the dummy node with prefix sum 0, we skip directly to the last occurrence of 0, which is node -2. At node -2, the prefix sum is 1, and since there are no further nodes, the traversal ends. The final list contains only -2. Lastly, let's briefly consider a third example with the input 1, -1, 2, -2, 3, -3. Here, during the first pass, the prefix sums map captures all prefix sums, but each subsequent prefix sum revisits a zero-sum subsequence, ultimately removing all nodes. In the second pass, the list is entirely skipped, leaving an empty list as the result. This demonstrates how the algorithm efficiently removes all zero-sum subsequences from the list, regardless of their position or length. To understand the time complexity of our solution, let's break it down into two main passes through the linked list. During the first pass, we traverse the entire list to calculate prefix sums and store the last occurrence of each prefix sum in a dictionary. The key operations here include updating the prefix sum and inserting into the dictionary, both of which are constant time operations under average conditions. Since we perform these operations for each node, the time complexity for this pass is O(n), where n is the number of nodes in the linked list. In the second pass, we revisit the list to adjust pointers and remove zero-sum sublists. Similar to the first pass, we update the prefix sum and perform dictionary lookups, both of which take constant time. Additionally, pointer adjustments are performed once per node, also in O(1) time. This means the time complexity for the second pass is also O(n), as each node is processed once. Together, these two passes contribute to a total time complexity of O(n). Now that we've established the time complexity, let's evaluate the space complexity. The main space overhead in this solution comes from the dictionary, which we use to store prefix sums and their corresponding nodes. In the worst case, where each node in the linked list has a unique prefix sum, the dictionary will contain one entry per node, leading to an additional space usage of O(n). Beyond this, the dummy node introduces a constant overhead, and other variables like the prefix sum and the current pointer use O(1) space. Therefore, the overall space complexity is dominated by the dictionary and is O(n). Combining these insights, we see that our optimized solution is efficient in both time and space, adhering to linear complexity in both aspects. When comparing our optimized approach to a brute force method, the advantages become clear. A naive solution would involve checking all possible sublists in the linked list to determine if their sums equal 0. Since there are O(n) squared sublists in the worst case, and calculating the sum of each sublist can take O(n) time, the total time complexity for the brute force approach is O(n) cubed, which is highly inefficient. The space complexity, however, is O(1), since no additional data structures are used. In contrast, our optimized approach leverages prefix sums and a hash map to reduce the time complexity to O(n), while using O(n) space for the dictionary. This trade-off of additional space for significantly reduced time complexity makes the optimized solution vastly more scalable, particularly for large input sizes. Finally, let's analyze the best, average, and worst cases for this algorithm. In the best-case scenario, the linked list contains no zero-sum sublists. Even in this case, the algorithm still performs two full passes through the list, resulting in O(n) time and O(n) space for storing prefix sums. In the average case, where the list contains a moderate number of zero-sum sublists, the time complexity remains O(n), but the dictionary may use slightly less than n space due to reused prefix sums. In the worst-case scenario, every node in the list has a unique prefix sum, leading to O(n) time and O(n) space, as the dictionary will contain one entry per node. Mathematically, each node is visited exactly twice, and all operations per node, such as dictionary insertion, lookup, and pointer adjustment, are constant time. This results in a total time complexity of O(n). The dictionary, which stores up to n entries, determines the O(n) space usage. In conclusion, this algorithm achieves linear time and space complexity, making it a highly efficient solution compared to the brute force method, which suffers from quadratic time complexity. When tackling this problem, there are several common mistakes to watch out for. First, not handling edge cases like an empty list or a list with only one node can lead to runtime errors. It's important to explicitly validate these cases to ensure your solution doesn't break. Next, improper removal of nodes is another frequent issue. If you modify the linked list without correctly updating the pointers, it can result in broken lists or even memory leaks. To avoid this, using a dummy head node can simplify pointer management and make the process more robust. Another pitfall is relying on nested loops without optimization. A naive O(n) squared approach can easily result in a time limit exceeded error on large inputs. Instead, leveraging the prefix sum technique combined with a hash map allows you to achieve an efficient O(n) solution. Finally, you need to be cautious about how you manage the prefix sum map. Reusing a prefix sum that has already been handled can lead to incorrect deletions. Make sure each prefix sum is stored only once for a unique node position, ensuring the correctness of your solution. It's also important to consider integer overflow when working with prefix sums, particularly in languages like Java or C++, where this can occur with very large values. Using appropriate data types or modular arithmetic can help prevent these issues. From an interview perspective, this problem is an excellent opportunity to demonstrate your ability to recognize patterns. Specifically, it's a linked list variation of the subarray sum equals k problem, and identifying the prefix sum technique is often key to solving it efficiently. Interviewers will likely expect you to improve upon brute force methods, so be prepared to discuss trade-offs between time and space complexity. Additionally, pointer management is critical because linked lists lack random access, so you need to carefully explain how you maintain the integrity of the list while modifying it. Lastly, you should be ready to describe how your solution handles edge cases, such as an empty list, a single-node list, or a list where the entire sequence sums to 0. Addressing these scenarios effectively can leave a strong impression. This problem also shares similarities with several related problems on LeetCode, such as subarray sum equals k, path sum 3, and continuous subarray sum. Recognizing these connections can help you understand the underlying patterns and techniques that are broadly applicable. When it comes to alternative approaches, the brute force method is the most straightforward. It involves iterating over all possible subarrays or sublists to calculate their sums and identify zero-sum sequences. While this approach is simple to implement, its n² time complexity makes it impractical for larger inputs. A more efficient alternative is the prefix sum technique combined with a hash map, which allows you to solve the problem in n time. This approach involves storing prefix sums and their corresponding nodes in the hash map, and if a prefix sum repeats, it indicates that the nodes between these occurrences sum to 0. While this method is optimized for time, it does require additional space for the hash map, which is a trade-off to consider. Another alternative to consider is recursive backtracking, which explores all possible subsequences to find zero-sum sequences. While this approach can be useful for conceptual understanding, its exponential time complexity of 2 to the power of n makes it highly impractical for real-world applications. Lastly, there's the two-pointer technique, which is effective in n time for sorted linked lists. By using two pointers to identify zero-sum sequences, this method is more space-efficient. However, it requires that the linked list be sorted beforehand, which limits its applicability to unsorted lists. Each of these approaches has its advantages and disadvantages, so the choice of method often depends on the specific constraints and requirements of the problem you're solving. Great job! We've successfully solved the problem and reviewed key concepts. Remember to practice similar problems to reinforce your understanding. Thanks for watching, and see you next time. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!